How can we modify our mathematical model to account for the effect of an atmosphere? And can we calculate the magnitude of the greenhouse effect? To do this, we need to know how radiation from the Sun and the Earth interacts with the atmosphere. We have described both the Earth and the Sun as blackbody radiators. We noted that the spectral distribution, that is the intensity of radiation emitted by a blackbody at different wavelengths, is simply determined by its temperature. Wien's law describes this relationship. It states that the wavelength of the peak of the spectral distribution is inversely proportional to its temperature. The solid red line and the solid blue line in the top panel of this figure show the spectral distributions, or blackbody curves, for the Sun behaving as a blackbody radiator at 5525 Kelvin and the Earth behaving as a blackbody radiator at 255 Kelvin. The solar distribution peaks at approximately 0.5 microns or 500 nanometers in the visible region of the electromagnetic spectrum. The terrestrial distribution peaks at approximately 15 microns in the infrared region of the electromagnetic spectrum. In the second panel, you can see the effect of the atmosphere. It can absorb at certain wavelengths but not others. The bottom panels separate this atmospheric absorption to the particular gases responsible. You can see that water vapour is the most important absorber, particularly at the longer wavelengths in the infrared. The solid red and the solid blue areas in the top panel identify the effect of atmospheric absorption on both solar radiation and terrestrial radiation. The first thing to note is that the atmosphere cannot absorb and radiate at all wavelengths and so cannot be treated as a black body. This differentiation in absorption properties of the atmosphere is important. At visible wavelengths at around 0.5 microns, the atmosphere is largely transparent. That is, it lets radiation in the visible to pass through without being absorbed. At shorter wavelengths, in the ultraviolet, particularly below 0.3 microns, the atmosphere is opaque. That is, it absorbs all radiation at these wavelengths. The reason for this is the presence of oxygen and ozone in the atmosphere. The absorption prevents potentially mutagenic radiation from reaching the biosphere. At infrared wavelengths between 6 and 25 microns, the atmosphere is also opaque. It should be noted that at some wavelengths in the infrared, absorption is not possible because there are no molecules present in the atmosphere that can absorb such wavelengths. This leads to the presence of so-called atmospheric windows. Radiation emitted by the Earth's surface at wavelengths in an atmospheric window will escape unhindered to space. This discussion of the radiative properties of the Earth's atmosphere predicts how the atmosphere will interact with the various radiations passing through it. Solar radiation at visible wavelengths will largely pass through the atmosphere unhindered. This radiation will be absorbed by the Earth's surface. The Earth's surface will then emit radiation at wavelengths dependent on its temperature, that is, in the infrared. The atmosphere will largely absorb all this terrestrial radiation. The atmosphere will also emit radiation dependent on its temperature, but it will not be able to emit at all wavelengths. This radiation is emitted in all directions. The component directed towards the Earth's surface acts as an additional source of energy and results in an elevated Earth surface temperature. The simplest way to extend our mathematical model to include an atmosphere is to treat the atmosphere as a single layer of uniform temperature. In this diagram, we can see the global average solar flux, that is the energy per unit area per unit time, impacting the top of the atmosphere. This is denoted F sub S. The fluxes from the ground and the atmosphere are F sub G and F sub A respectively. Note that the total emission from the atmosphere is twice F sub A to account for radiation emitted upwards and downwards. To complete this model, we also need to account for the absorption of radiation by the atmosphere. We will do this by defining transmittance as the fraction of radiation that isn't absorbed. The solar transmittance is given by Tor sub S, and the terrestrial transmittance is given by Tor sub G. So the amount of solar radiation that passes through the atmosphere to be absorbed by the Earth's surface is simply F sub S times Tor sub S. Similarly, the amount of terrestrial radiation that passes through the atmosphere to space is simply F sub G times Tor sub G. To begin, we need to calculate the solar flux. To make things easier, we will take into account the albedo and the ratio of the cross-sectional area of the planet to its surface area in this calculation. This leads to a value for the solar flux of 240 watts per square metre. If we assume that the temperatures of the Earth's surface and the atmosphere are constant, that is, that the system is in equilibrium, then the fluxes must be in balance both at the top of the atmosphere and at the Earth's surface. At the Earth's surface, the incoming flux is the sum of F sub S times Tor sub S and F sub A. This must be equal to the flux leaving the Earth's surface, that is F sub G. At the top of the atmosphere, the incoming solar flux must be equal to the flux leaving the top of the atmosphere, that is the sum of F sub G times Tor sub G and F sub A. We now have two equations. These can be quickly solved to eliminate F sub A to give the expression shown here. Does this expression make sense? It relates the terrestrial flux to the solar flux and both the solar and terrestrial transmittances. Treating the Earth as a black body, we know that the terrestrial flux is proportional to the fourth power of the Earth's surface temperature. The greater the terrestrial flux, the greater the Earth's temperature. Okay. What happens in this expression if the different quantities change? If the solar flux increases, the terrestrial flux will increase and the Earth's temperature will be higher. That makes sense. Similarly, if the solar transmittance increased, more solar radiation would impact the Earth, increasing the Earth's temperature. Again, that makes sense. Finally, if we decrease the transmittance of terrestrial radiation, for example, if we were to increase the amount of greenhouse gases in the atmosphere, then this expression would lead to an increase in the terrestrial flux and thus an increase in the Earth's surface temperature. So this single layer model explains how changing the amount of greenhouse gases can lead to global warming. But can it predict reasonable Earth surface temperatures? To calculate the terrestrial flux, we need representative values for the solar and terrestrial transmittances. Appropriate estimates are 0.8 for solar transmittance and 0.1 for terrestrial transmittances. Substituting these into our expression, together with the solar flux, gives a terrestrial flux of 393 watts per square metre. If we use the Stefan-Boltzmann law, we can calculate the Earth's surface temperature. This value for the terrestrial flux leads to an Earth's surface temperature of 289 Kelvin. This is equivalent to 16 degrees Celsius. This means that the Earth's surface is 34 Kelvin warmer than it would be without an atmosphere. This is the magnitude of the greenhouse effect. Thanks for listening.